So, good morning, one and all. So, we are going to start our 21st Transpedia talk series. Over to you, Philip.
A very warm good morning to one and all present here. I am Mclean Jojo, Project Fellow NATPAC, and it gives me immense pleasure to welcome you all to the 21st talk of Transpedia Research Talk Series organized by KSCSTE National Transportation Planning and Research Center, NATPAC. This talk series is yet another unique venture of NATPAC designed to explore diverse topics from the cutting-edge technologies to sustainable solutions. Here, we will be featuring eminent young researchers to share their valuable insights for kindling the spirit of future research and development in transportation. Today, we have with us Dr. Ashith Marath, Research Engineer, Turner-Fairbank Highway Research Center, Federal Highway Administration, USA, for sharing his valuable insights on the topic, from lab to field, the role of accelerated pavement testing in modern pavement design. Now, I request Sri Anish Kini, scientist, to deliver the welcome address.
Good morning, one and all. As mentioned earlier, KSCSTE-NATPAC has launched a technical discussion series named Transpedia Talk Series, which is envisioned to promote research for shared benefits by disseminating knowledge on diverse topics from cutting-edge technologies to sustainable solutions. This is intended to bring in a platform for young researchers across the globe to connect and interact to better shape the future of research and development in transportation. The inaugural talk of the series was conducted on 24th August 2023 through online platform, where more than 200 participants from eminent institutions, departments, etc. attended. The inaugural address was given by Professor Dr. Tom V. Matthew, Chairman, Research Council, KSCSTE-NATPAC, and Professor at IIT Bombay. Over the past year and a half, 20-odd sessions have been successfully conducted, covering a wide array of topics in the field of transportation. Today, the 21st talk in the series will be delivered by Dr. Ashith Marath, Research Engineer, Turner-Fairbank Highway Research Center, Federal Highway Administration, Mclean, USA. It is a great pleasure that I extend a warm welcome to our distinguished speaker, who has graciously accepted our invitation to share insights and knowledge on the topic of from lab to field, the role of accelerated pavement testing in modern pavement design. After the presentation, we'll have a question and answer session where you can pose your questions and engage in a meaningful dialogue with Dr. Ashith. Feel free to participate actively. Once again, thank you for being here today, and let us give our warmest welcome to Dr. Ashith Marath as we eagerly await the key insights he is about to share. In addition, I would also like to welcome Professor V. Raghavan, former professor at IIT Madras, who is also attending the talk. Thank you.
Thank you, sir, for your welcome note. Now, I would like to invite Sri Ashith Asad, Junior Scientist, to introduce the speaker to the audience.
Thank you, Mclean. Dr. Ashith Marath completed his PhD in Civil and Environmental Engineering from Rowan University, USA in the year 2024, under the supervision of Professor Dr. Yusuf Mehta. Dr. Ashith completed his MTech from IIT Bombay in 2020 and BTech from TKM College of Engineering, Kollam, Kerala in 2017. He is specialized in pavement materials, accelerated pavement testing, electrically conductive asphalt systems, and climate resilient infrastructure. During his doctoral research, Dr. Ashith worked on multiple projects funded by the US Army Corps of Engineers, including full-scale evaluation of electrically heated asphalt pavements for de-icing application. Also, he worked on numerous other projects such as the validation of force model for whole region pavement design, etc. His research is mainly focused on the development and evaluation of innovative pavement technologies through full-scale testing, sensor integration, and performance modeling. He has more than 18 publications in reputed journals and conferences. Over to you, Dr. Ashith, for your technical talk.
Thank you.
Sorry, Dr. Ashith, we can't hear you. I think you're on mute.
Hello.
Yeah, now you're audible. Sorry, still, Dr. Ashith, sorry to interfere. Still can't hear you.
Am I audible now?
Yeah, you're audible now.
All right. Okay. Yeah. So usually we use Microsoft Teams. So this is the first time I'm using WebEx in this PC. So I was just getting some confused. So let me share my screen first with the presentation. Can everyone see the slide?
Yeah, it's
Title
visible.
slide? Yeah. Okay. Okay. All right. So thank you for this opportunity to present my research. And I know like this series normally like the presenters do present their PhD research mainly here. But in my case, I thought like it would be better to talk more in kind of a general topic rather than going in depth into the PhD research, specific PhD research topic. Especially my PhD research is kind of a niche area, like which is not applicable for all the places. It's only dedicated for cold regions. So I thought like I'll stick with the somewhat like more general topics and which might be helpful for and new information for at least some of the peoples in the audience. And I'm happy to see like some of the like professors, Dr. Samson Matthew and Viragan sir here. So and I want to make a small correction here. So, introduction. So, I work as a contract research engineer in Turner-Fairbank. So, as non-citizens, we are not allowed to work as a direct research engineer under the government. So, that is a slight correction. So, with that being said, I'll start my presentations. Let's move on to the slides now. So, and again, so in this presentation, I will be presenting mainly kind of a broad overview of the APT facilities, what we have mainly focused on the APT facilities in the US, and also the facility what we have at the Turner-Fairbank Highway Research Center. And so for those who are like really interested to know more in-depth details, feel really free to reach out to me directly. I'll be sharing my email ID at the end of the slides. So with that being said, let's move on to the slides. So what is accelerated payment testing? So I thought of putting this slide as the first slide because in India the APT facility is not that much a common facility which you see with the associated with the universities of or research centers. I know there is a APT machine purchased by Central Road Research Institute in Delhi, but from my understanding, I think they are not using it very actively. So I thought like to give a very general introduction about the accelerated payment testing. So according to Professor Powell in Auburn University, the definition for APT goes like this. It's a controlled application of a prototype wheel loading at or above the appropriate legal load limit to a prototype or actual layered structural payment system to determine payment response and performance under a controlled accelerated accumulation of damage in a compressed time period. So it's a long sentence, I know. So to break it down, it is basically a application of a prototype wheel loading over a structural payment system to determine two things. That is, one is the payment response under wheel loading, and also the payment performance for long term. And very importantly, under a short time period. So that is the main feature of APT facility. And so the key component of an APT facility is the machine what you see on the right, which is normally called as HVS, Heavy Vehicle Simulator, but it depends on the manufacturers. Some manufacturers call it as Atlas, and some of them call it as HVS. But for this presentation, I will just call this machine as an HVS, Heavy Vehicle Simulator. So this is particularly this machine is from research facility by Federal Aviation Administration. So what this machine, the main component of this machine is a carriage. So right here in this machine, there you can see a carriage here at the very end, and this carriage will have a wheel attached to that, and this wheel is adjustable. Like you can put any kind of wheels. For example, FAA uses aircraft wheels, which has a completely different configuration. And for the FHWA purpose, we use normal truck tires. It could be single tire or dual tire assembly. And the machine has a control system here, and where you can control the load application, speed, and also the tire pressure of the wheel. So these three are the main three features of a traffic loading which we use for the design, right? Payment design, right? So we can control all the three parameters. And also some of the HVS has the facility to control the temperature of the payment. So basically it will be by a insulating cover on both the sides, and there will be a heater inside inside this area, so that we can precisely control the temperature of the payment layers. So with that being said, let's move on now. Why the APT matters. So the main advantage of using APTs is to validate new materials or designs before recommending for widespread use, and help to understand why certain payments fail prematurely, and improve specifications and also construction practices. I included the construction practices because for doing the APT facilities, you need to go through all the steps of constructing a typical highway or payment section, that is including the planned production, right? So that helped us, especially in my experience, that helped us a lot with identifying the challenges in planned productions, especially when you use new materials. So that was really a helpful process which comes as part of the APT testing plan. So, and finally, a APT facility lets us to understand the payment mechanical behavior, and eventually improve the payment prediction models. So now I'll go through that one by one, each of the features I mentioned now. So first, let's move to understanding the role of APT to understand payment mechanics. So in Turner-Fairbank Research Center, this is one of the main focus for us to evaluate the payment mechanics with the help of multiple different kinds of sensors embedded in the payment. So we, especially in our case, we have 11 test sections. Each test section has 4 different test sites, and so combinedly it will be 44 test sites are there, and each entire 11 lanes are embedded with almost 300 to 350 sensors are embedded in that, including pressure cells and strain gauges. I will explain that in the coming slide. So with all these responses from these sensors, we are trying to capture the variation in the stresses and strains under different wheel loading and different configuration, the pavement temperature, wheel load and pressure and speed, all these different configurations. And also this supports evaluation of load-induced deformations. So especially in understanding or to measure the progress of rutting or the cracking phenomena. So we continuously evaluate that to understand how the cracking is propagating or the rutting propagating in the pavements. And enables monitoring of fatigue and rutting mechanisms. So this again, this is the one of another main idea what we have with our current project to investigate the propagation and mainly focusing on the fatigue cracking propagation. So how it initiation and different stages of the cracking. And also this APT facility facilitates a validation of structural response models. So basically we for the pavement design in mechanical empirical pavement design in the US, we use linear elastic analysis as the basic pavement response model, except for some of the design software such as IllyPave and FlexPave. The Astroware, which is kind of most widely used software, uses linear elastic analysis. So we use our payment responses, recorded payment responses, to validate these linear elastic analysis or finite element analysis uh, to validate the prediction accuracy of these models. And so I have shown in a small example from one of our test results, one of our sensor results. So we have out of 11 test lanes, two of them is inverted payments. As some of you might be familiar with the inverted payments, for those who are not, it is basically a conventional asphalt pavement structure with a sub-base layer constitute of a cement treated base. So it will have two stiffer pavement layers, and the base layer will be sandwiched. The base will be an unbound aggregate layer, which will be a sandwiched layer between the asphalt and a stiffer CTB layer. So on the right side, you can see the graph shown here. So I have the legends are lane 5, 6, and lane 11, right? So lane 5 and 6 are conventional asphalt pavement, and it is the same pavement structure except the type of asphalt mixture used. One has a polymer modified binder, and the other one has a conventional pavement asphalt binder. So if you look at these plots here, so these data points here are the pressure values. So the y-axis is the difference between pressure, vertical pressure at the base and sub-base layer. So here you can see the star dots here, two dots are there. So that is the location where we measure the vertical pressures. So the y-axis shows the difference between these pressures divided by the thickness of the base layer. So the idea was that the y-axis, you can think it as a representative of the modulus of the base layer. So if you assume a conical, like a linear conical distribution of the stress along the depth, so this can be considered as a representative of the modulus of the base layer, and the x-axis is the base pressure at the vertical pressure at the top of the base layer. So as you can see clearly, there is a stress dependency on the modulus of the base layer. And when you compare the conventional pavement, that is for the lane 5 and 6, to that of the lane 11, that is the inverted pavement, you can see a clear difference in the trend here. Whereas like both, all the three lanes have the same base layer material. Because of the CTB layer at the below the base layer, the behavior of the base layer, the modulus of the base layer is different with respect to the pressure experienced by the base layer material. So with this kind of analysis, we are able to use better models for our payment prediction, response prediction, and also for our back calculation procedure using the FWD testing. So so these kind of analysis we do with our sensor data, so what we collect from our test sections. And moving on further, so another application of the APT is to calibrate the payment design models. So which is mainly for the PMED. PMED stands for Payment Mechanistic Empirical Design. So the general process, I will classify it as 5 steps. So first one is a run APT test on instrumented sections. And second step is to characterize materials in the lab. And the third step is to use mechanistic empirical software such as CalME or MEPDGware, Astoware to predict performance using lab data and compare prediction to APT measurements such as rutting, cracking, and deflection and strains, and adjust the model calibration factors, that is the transfer function, until prediction matches the measurements. So for example, like the California DOT has developed their own rutting and fatigue models which is more suitable for the California region. And I'll talk a little bit about transfer functions. So for those who are not familiar with what are those functions. So moving on to that, yeah. So this is a very simple, basic structure of the payment mechanistic empirical payment design. So these are the steps actually. So first step is you characterize the payment materials in the lab. By characterization, I mean to measure the mechanical properties, to determine the mechanical properties of the mixture, not necessarily index tests such as like ideal CT or a test like that, which are basically the index based test. Instead of that, what I mean is that one of the example is the dynamic modulus, which is a fundamental property of an asphalt mixture, which we widely use in the payment mechanistical empirical design approach. So once you characterize the materials, you are using some payment response model, which could be linear elastic analysis. So in our case in India, we use IIT Pay, which runs on a linear elastic analysis program. And it could be a finite element analysis program as well. And the output from the payment response model will be the stresses and strain within the payment structures. And more specifically, like we focus as payment engineers, we focus on the critical location, that is for the strains at the bottom of the asphalt layer, and also a vertical strain at the surface of the subgrade layer. So now you have the stresses and strains with you computed using the response model. But now how to connect these stresses and strains to the actual payment distresses, that is cracking and rutting. So there comes the transfer function. So the transfer function uses the stresses and strains. So those are basically equations which are developed mainly based on regression analysis, and these stresses and strains are converted to the payment distresses using the transfer functions. So this part of the PMED is the empirical part here. So this is the empirical part in the PMED, and this portion, the response model and determination of stresses and strains, comes the mechanistic part of the design. So with that in mind, and let's move on to another application of APT, which is to develop correlation between index-based test and the payment performance. So the APT correlates like lab index properties to in situ behavior. It uses APT to evaluate how index tests reflect the mechanical performance of subgrade, base, and surface layers, and also enhances the reliability of material selections. Confirm whether the lab tested parameters like CBR or resilient modulus align with the field responses under loading. I have given a graph here on the right side, which is again from our test facility in Turner-Fairbank. So this was a result of one of our previous study, which shows the crack length, cumulative crack length with respect to the ALF passes. So here the ALF means it is accelerated loading facilities, which is same as the PTF. Like earlier we used to call it as a ALF. So it's similar as the APT. So what the study done was that they tried to correlate the Illinois flexibility index test results with the cracking results you usually see in the figure. And the result was that the IFIT was consistent in ranking the APT field cracking performance and indicating a high discrimination potential. Yep. So with that applications being said, so the main feature of the APT that I mentioned is the loading mechanism. That is the main feature of an APT facility, which distinguishes between each facilities. So on the left side figure, you can see a circular test track. And this is one of the facility from France, which is called as IFSTAR. And this test section has a rotating arm-like structure, which has an adjustable radii of this wing so that they can load different lanes simultaneously. And these kind of facility are more useful in case of requiring a higher speed of loading. That is one of the main advantage, because in HVS machines, like similar machines like this, since it needs a back and forth motion, you cannot achieve a very high speed with these kind of machines. But for that application, you need to go for either a circular restrictions or like a manual driven truck structures, like what you see in the right top figure. So this is a image from the NCAT facility in Alabama. So they have a test track, like, which is very long test track, and they have a truck which was pre-loaded with weights, and this was driven manually by a driver. Like I'm not sure like how long a day they drive, but it's continuously driven by a driver. And the bottom side, you can see two machines. These are my favorites because this is the one in our facility which I work currently now. And the right side, the bottom right part, is the HVS machine used in Robin University, where I used to work a lot during my PhD dissertation. And I move on to the another important aspect of an APT facility, which is the instrumentation of payment layers. So most of the APT facilities, I have seen like they won't give much attention to the installation of the sensors in the payment. But in my understanding, this is one of the most critical step during an APT construction. And the reason is that once you install these strain gauge, the sensors in the payment, there is very least chance that you can make any corrective actions to those installations. So you need to be very careful when we do the installation of the sensors. And the common sensors which you can see in most of the APT facilities is the strain gauges. From the name itself, it says like it measures the linear strains in the payment structure. Normally, we use it in the asphalt layers, to especially at the bottom of the asphalt layer, as that is the critical location for the payment design. And so the image here on the on the very rightmost portion shows a typical asphalt strain gauge used in our facility, and the next one is the pressure cells. So the pressure cells, these are the images of the pressure cells, and this comes with two different sizes. So that should be selected based on the need of the project. And deflectometers, these are the deflectometers. So normally deflectometers are not embedded in the payment. In the same case, like all the other sensors are embedded sensors. So these deflectometers generally, you might be familiar with the falling weight deflectometer device. So there they use deflectometers to measure the deflection of the payment under impact loading, which is basically geophones which measure the velocity of the payment under an impact loading, and which calculate the deflection by integrating the velocities. So, and finally, the temperature and moisture sensors, which are very crucial for the payment analysis. And on the bottommost portion, you see the image of the moisture sensors, and most of the moisture sensor has a capability to measure the temperature as well. So what the sensor do is it measures the permittivity of the soil. So normally we install it in the unbound granular layers, and which measures the permittivity of the soil, and you need to have your own like calibration equation. So it depends, the calibration equation depends on the materials you use. So you need to develop your own calibration equation to estimate the moisture content from the permittivity measured by the sensors. So with that being said, I will move on to the APT distress detection. So you might be familiar with the NSV vehicle, the network survey vehicles, which is used in the. I think there are some projects in India as well, like we use the NSVs. But in our facility, we don't use a full scale NSV. Instead, we use a small level which has a single unit of laser sensor, which is attached to a computer component and power supply. And these small cards we use to do the scanning, laser scanning of the payment. So which gives a 3D image of the 3D data of the payment surface. So, and this is further processed to detect the cracks and all other distresses, including retting and macro texture of the payment surface. And earlier we used to do visual mapping for the cracking. So we used to go to the field and put a transparent sheet over the test sections and mark it manually every time, like every interval of specific passes of the HVS. And now we have moved on to automated images. So the HVS itself have a camera system which captures the image of the payment, and using a neural network model such as YOLOs. So these images are processed to detect the cracks over the payment structure. So the one of the drawback of that system is that it cannot, like, we cannot detect the depth of the crack using such kind of 2D image sensing. So that is the reason we go with the LCMS device. By LCMS means these devices.
നമ്മൾ ചെയ്തിട്ടില്ല ടെൻഡറിന്റെ അല്ലേ
Hello.
നമ്മളധികം പ്രൊഫൈലൊന്നും ചെയ്ത് മിക്കവാറും കളിക്കാറില്ല. അത് കഴിഞ്ഞിട്ട് നമ്മൾ മിക്കവാറും ഇല്ല നോക്കില്ല. മറ്റേത് ആന്റോ ആന്റോ ചൊവ്വ.
Ashith, you may continue.
Okay. Yeah. So, so on the right side, so this is the LCMS laser cracking measurement system. As I said, the main reason to use this device is to we need to get the depth of the cracks as well. And so, and another thing, like we do it as a side work, not as our main objective. So that is the validation of these devices. So for a network level evaluation, this works well. It is perfect to do that. But we are trying to improve the algorithm, their detection algorithm, so that it can be applicable for a research facility as well. So that like in a research, unlike network level survey, we in a research level study, we need to detect the cracks at a very fine level itself. Like we need to detect the cracks at a when they find cracks like hairline cracks develop, and we need to detect the propagation of the cracks. So we are trying to fine tune their algorithm and also to improve their prediction model to detect these kind of finer levels of details. And finally, like for the we do the, at the end of the loading process, we do forensic evaluation by taking this is very typical in all the facilities. We take the core across the crack and determine like what kind of cracks and what is the depth of these cracks are. So with that, I'll move on to the rating evaluation. So for the rating evaluation, we uses a laser profiler, which is typical in most of the APT facilities. And we have two devices. We have a standalone laser profiler device like this, what you see in the image. And also we have an integrated laser device on the HVS machine itself. So once the HVS has completed specific number of passes, it is programmed to automatically record all the like profiles at every 1 meter interval. So that is the way which we measure the rating of the payment, and which is very much accurate. Like the we could get an accuracy in millimeters with its kind of sensors. So and the main analysis with this value, the rating value from the laser profilometer will be to plot it against the number of wheel passes, to just see the what is the propagation rate and what is the different phases of a rating propagation. And we also try to separate the rating. As you know, rating could happen from two cases. So one is the rating occurring in the subgrade layer or even the unbound layers, any unbound layers, and also rating happening by the densification of the asphalt layer. So we try to separate it by using some kind of survey markers. We call it as survey markers, and that will be a steel plate placed below the asphalt layer, and there will be a small hole drilled to that plate, and we try to measure that using a vernier caliper at every interval of the HVS passes, and this will give you the using that measurement, you can distinguish between what is the rating caused due to the densification and also the rating caused by the unbound payment layers. So with that being said, yeah, and finally the structural evaluation in the in our APT facilities. So the right side image is the falling wave deflectometer we use currently, and this is actually a modified version of the typical falling wave deflectometer. Because the older version used a hydraulic system for loading applying the impact load on the pavement. So this one is completely electronically controlled. So the main advantage of this new version is that it is much faster than the previous one, because it avoids the continuous the following hits of the individual loading. So once you load the payment, the machine captures the load at the same time, like at the same time it hits the payment and come back. It will not have multiple impacts at a single drop. So that reduces a huge time in testing the payments, and this is very fast in that way. So we recently upgraded this. So this is called as fast FWD. And we also have a LWD. We use this as a LWD device to to test our payments. The reason is that this can be this is very fast, and also we can do the LW testing under the HVS machines. To do the FWD testing, we need to move the machine to sideways, and it is too much of work hours. So because of that, we still continue to use the LWD testing. And LW testing is typically used for unbound payment layers, but in our facility, we still use it over the asphalt payment surface as well. So, I have listed some of the testing facility, APT facility, which are kind of well known across the globe. So, the first one is the Turner-Fairbank, and where I currently work, and Rowan University has creates, and the Federal Aviation Administration as a test facility in Atlantic City in USA, and NCAT test track. You have seen already seen couple of images which I presented, and also Minnesota DOT has a APT facility which mainly focuses on concrete payments. And in India, we have CRRI, as I said, and I'm not sure like how well the research is going with HVS there. You guys may know better than me. That's a case. So yeah. So moving on to the APT performance results. So the idea is to show some of the impacts of the APT, like how the different APT facility has used the APT to have meaningful results at the end. So this one, like focusing on the rating, the goal was to find lab tests that reliably predict the field rating conditions. So this test was conducted by NCAT, and their findings was the dynamic creep was a poor predictor and couldn't rank mixes with different gradations correctly, and didn't predict the low void mix failures. And they also found that the wheel tracking testing, such as the Hamburg wheel and the APA tests, were correlating well with the field rating values, and they tried to use the APT to distinguish between two different materials, and which is called as a GTR material, and the other one is the SBS material, which is the polymer for the binder modification. And coming to the cracking performance, so the in one of our previous tests in Turner-Fairbank, we tried to correlate the binder properties, that is G star sign delta, to correlate that parameter with the fatigue cracking performance, and found that the G star sign delta was a poor predictor for the cracking performance, and also found that CTOD parameter test showed strongest correlation with APT fatigue results, and also the binder yield energy was also promising. And again, the NCAT mixture test, like they evaluated the energy ratio concept, was validated using the APT facility to predict the top-down cracking susceptibility of the payments. And another applications by NCAT test track is they used their APT facility to demonstrate the high wrap mixture performance. So they used a good they demonstrated good performance of like 45 to 50% wrap usage in the mixers, and also they used the APT with warm mix asphalt payments and showed comparable performance to hot mix asphalt, leading to state approvals. And also they validated the Stone matrix asphalt, which allowed use of local aggregates like crushed gravel for widespread use in the state. And the Florida DOT has done some interesting studies with their APT. So try to use a different polymer modified binders in the payment to optimize the placement depth. And also they try to use the PG 8222 binder evaluation, investigating the stiffer binders for high stress areas, intersections. And they also try to check, see the, instead of the pavement material side, they try to use different different tire configurations, and they try to evaluate between the wide base tires and dual tire assembly. So wide base tires are kind of replacing the dual wheel assembly because of the lesser wheel weight, and it can carry almost the same load as that of the dual wheel assembly. So they try to evaluate the impact of the wide base tires and found that it is similar impact as that of the dual wheel assembly. And with these aspects of the APT facility, I will now go through my one of the case study, which is basically my PhD dissertation, so which has the APT as one of its major component. So the title of the study was a demonstration of electrically conductive asphalt pavements for de-icing application in cold regions, and it was conducted at our APT facility in Rowan University, and the project was funded by ERDC, which is a R&D division of US Army Corps of Engineers. And so now I will go through the background of the study and objectives. So, as I said, this is kind of a very niche area, not applicable for all like full length highways. So the motivation behind the US Army Corps for this project was that to implement this for their airstrips in cold regions, extremely cold regions. So not for highway applications. So the current practice of snow and ice removal from the surface is the use of de-icing salts and chemical de-icers or mechanical plowing. So here in the US, this is if you have visited US in the winter, you could have understood this, like the accumulation of snow is a major issue in the US, and the government spends a lot of money on like maintaining the pavement surface clear during winter season. So it's a major issue here. So so the removal of snow is extremely like time consuming and also labor intensive process. So the idea of electrically conductive pavement is to generate heat through the conduction of electricity within an electrically conductive asphalt layer, which is called as an ECA layer. And so the concept is simple, like, so it's basically how a iron box is working, right? So we conduct electricity through a material which has a conductive property, and it generates heat according to Joule's law of heating. So with that, then so these kind of pavements are supposed to have ability to prevent the accumulation of snow and ice formation over pavement surface. So on the right side, you could see the typical structure of the ECA pavement, so which has a base layer as the conventional pavement, which could be unbound or bound layers, and there will be an electrically conductive asphalt layer, which will be between the asphalt surface layer and the base layer. And there will be electrical power supply to this conductive layer, and as it conducts the electricity through the conductive layer, it generates heat and propagates towards both sides. So normally we expect the more heat conduction will be to the upward side, because in winter seasons, like the asphalt surface have more colder temperature than the base layers. Because of that, more heat flow naturally occurs towards the upward direction of the pavement. So with that, the laboratory phase, I just included a single slide for the laboratory phase of the study. So which is basically to develop the ECA mixture, electrically conductive mixture. So the components of the mixture is the typical components such as asphalt binder, coarse aggregate, fine aggregates, and conductive additives. So conductive additives gives the property of the electrical conductivity to the materials. And in my study, I used graphite and carbon fibers as the conductive additives. So if you look at this, you have two types of conductive additives: carbon fibers in the fibrous form and graphite in the powder form. So the reason to use these two different kind is to balance the mechanical and electrical performance of the mixtures. So as you add more and more graphite into the mixture, it will start losing the cracking performance of the mixture. So in order to compensate that, we had to use certain doses of carbon fibers so that to reach at a balance between the mechanical and the electrical performance of the mixture. So in the lab on the right side, you see how you measure the electrical conductivity of the asphalt mixtures using a multimeter. And once the resistance of the mix is determined, we using the equations, we estimate the resistivity of the material. With that, so once we determine the electrical conductivity of the asphalt mixture, we moved on to the design phase of the payment, full scale payment. So I used a finite element modeling, which is only on the thermal side of the modeling, not the mechanical analysis. So I developed a thermal model for the de-icing payment, which can predict the payment temperature under different ambient conditions. And as you can see in this figure, in this image, you see this is the image from the test section constructed at Rowan University. And you can see the steel bars placed in transverse direction. So these steel bars are a main component of electrically conductive payments, which provides the electrical potential difference to the conductive layer. So the electrically conductive asphalt mixture will be placed right over this network of steel bars, and the electrical power supply will be connected to the one end of the steel bar network, so that it provides the electrical potential difference. So using the finite element modeling, I came up with a design chart for determining how much heat power output is required during different ambient temperature conditions, and using the required power output, what is the electrode spacing. I call these steel bars as electrodes. So what is the electrode spacing and what is the thickness of the conductive layer to be applied for the ECA payment. So with that design charts, we designed the payments and constructed test sections in our APT facility in Rowan University. And these are some of the images from our planned production of the electrically conductive asphalt mixtures. So as I said in the first slide, in the initial slides, one of the main advantage of the APT is you can also determine the production challenges, right? So this was very insightful for us, because we tried to on the left side image, you can see the mixing of the graphite and carbon fibers into the aggregates, and we tried to mix it with I tried to mix it in plant, and also you can see what is the kind of blending of this carbon fiber and graphite. Everything was fine at this stage of production, and once we arrived to the mixing stage, and we saw a lot of loss of conductive additives at the conveyor belt because of the presence of the graphite. The graphite has to stick with on the surface of the conveyor belt, and it was sliding. The conductive finer portion of the mix was sliding downwards, and it was not carried over upwards by the conveyor belt. So this resulted in a very high reduction in the electrical conductivity of the mixtures what we are seeing. So these kind of things, we were not able to capture it during our laboratory phase of study, and we had to compensate for the loss of conductive additives at the plant in order to achieve our target electrical conductivity of the mixtures. With that being said, we constructed the test sections using the mixtures, and we connected the constructed payment section to a power supply. And the image on the left, you can see how the payments performed during a snowfall event in New Jersey. So as you can see in the image, the payment was successfully able to maintain a snow-free surface. Like you can see the intensity of snow on the other side of the pavement, like how thick the snow was accumulated, but the sections were performing really well, maintaining a snow-free surface. And the right side shows the infrared image of the pavement surface. And as you can see here, there is a gradient, right? So on this portion, you can see a much higher temperature compared to this area. So the reason is that these two are two different electrically conductive pavements, and I mean like two different design configurations. And at the end, what you see is it is the conventional payment. We have a conventional payment here as well. So with that, so as we evaluated the de-icing performance of the payments, we moved on to the mechanical performance evaluation of the test strips. So there we use our HVS machine, and for loading the HVS machine, we had the target load of 40 kilonewton, which is typical for the truck loading, and tire pressure of 100 psi. And we had embedded sensors in the pavement, which is asphalt strain gauges and pressure cells. And it was a bi-directional loading mode. That means like the load will be applied in both the forward and backward direction of the wheel movement, and there was a wander applied. So and again, this is another feature for the HVS. So the HVS has the feature to do the wandering. So it can be you can give any distribution to that, like it could be uniform distribution across 8 inches, or normal distribution across 8 inches. So we, for this specific project, we applied a normal distribution across 8 inches of wandering. And the temperature was fixed at 50 degrees Celsius. And you see, as you can see here, there was these are the insulation covers on both sides of the machine, so that like you can maintain a pretty accurate temperature inside the machine, and as well as the surface of the pavement. And the target number of passes were 300,000 passes. And the testing plan was to conduct SWD testing. So again, the SWD is heavyweight deflectometer, which is typically used in airport runways, which basically it has a higher loading level than FWD. So we had an SWD in our facility, and the plan was to conduct SWD testing before HVS loading and conduct the HVS loading. And as the loading progresses, we took multiple measurements of the profile, using the laser profiler to measure the permanent deformation on the pavement. And at the end, we again did the HWD testing to compare the before and after loading conditions of the pavement. The figure shows the SWD device in Rowan University, and so these are the locations. We selected 3 locations, 4 locations within the wheel pass area, and we compared the pavement deflection. As you can see here, there are 2 different colors. So the red color indicates the deflections, SWD deflection after loading. The blue color lines indicates the before loading conditions. So we compared the deflection results in order to evaluate the pavement performance or the structural integrity as the HVS progressed. And the overall, like the the summary from the FWD analysis was that all the payment sections were, all the ECA conductive payment sections were either comparable to the conventional payment or better than the conventional payment performance. And we didn't do a back calculation analysis using the SWD deflection. The reason was that it had a PCC slab below the payment layers, below the asphalt layer. So because of that, it is kind of composite payments, right? So the back calculation process is going to be really hectic. Like we cannot rely on the results of back calculated modulus in that case. So we didn't go to that level of analysis. We stick with the deflection analysis and also like the deflection bowl parameters as well. Yeah, so yeah, and the laser profilometer was done at 3 different positions, and the results was like almost like all the 3 payment test strip had almost negligible rutting. If you look specifically to the values, like you could see like a minor increase in the higher value for the permanent deformation in the test strip 1, which is the control section, and the ECA payments were having negligible permanent deformation. And finally, the strain gauge reading. So as I mentioned, we installed longitudinal strain gauges. So we tried to use the peak tensile strain values and plot it against the number of HVS passes. So the idea was to look at the susceptibility to the fatigue cracking of the payments, and also remember that we didn't found any cracks at the end of 300,000 passes of the loading, and but we still use the peak tensile strain values to compare between 3 different payment sections, and we found that the ECA payments either had a comparable peak tensile strain value or even less than the conventional payments tensile strain value. So which is best in case of a fatigue performance. So. And finally, I think this is my last slide. So this is about the cost of APT. So I understand like the main reason which most of the agency which doesn't adopt an APT is because of the cost implication. So as you could guess, like these machines are pretty much expensive. So there are certain studies which by different agencies, they have done the benefit cost ratio. They have estimated the benefit cost ratio to evaluate evaluate the feasibility, economic feasibility of using an APT. And as you can see here, by Louisiana or Minnesota or South Africa, or the California DOTs, all of them has reported a PCR value like higher than 1, which indicates a good feasibility. So with that, I'm going to summarize my slides. So the main takeaway of these slides is that how the APT is impacting or contributing to the payments, payments in the payment network, right? So there are 4 key points: to develop a correlation between laboratory index-based test and the payment performance, and improvement of the mechanistic payment response prediction models, and development of empirical, that means the transfer function models to link payment responses to actual distresses. And finally, to improvement of the construction practice, especially in case of innovative materials, and also validation of non-destructive testing methods or technologies. So that's all I have for today. And As I said, feel free to ask any questions, and if any in-depth details are required, feel free to contact me in this the given email ID. Yeah, I'm open for questions.
That was an informative session. Thank you, sir. Now the forum is open for discussion.
Yeah, Dr. Ashith, this is Gautam. It was a nice presentation.
Thank you.
Yeah, actually, Virago sir present here for some time. I mean, for some time back, but it's my personal visit, so he had to leave a little early.
Okay.
However, he has mentioned few questions actually. Maybe I'll put in the chat box also.
Okay.
Shall I read it out?
Yes. Let me try to open the chat box once. Okay. All right. So, yeah, there are seven questions,
Yeah,
right?
sure.
All right. Yeah. So, I will. Okay, I will go through that one by one. Okay. So the first question is in APTF, the test section is constructed under ideal conditions of quality. The payment is not constructed as per actual practice or quality of construction. How will the result from APTF simulate actual field construction quality and performance? Theory to practice. All right. So yeah, so I agree with Veeraragan sir's comment, and in my experience, he's right in the when I think about the construction in Robin University, and it was extremely a controlled like a controlled condition, ideal condition of quality, because it was a kind of pilot study. It was not implemented in a full scale level. But in case of a test facility in a PTF, the Turner-Fairbank, our facility, the current facility, it was like we followed like the construction practice was as much as possible closely to the field practice, and we could see that like even like we were trying to get a accurate level of like precise level of asphalt layer thickness, and we were not able to achieve that. There was some level of variability within the asphalt layer thicknesses, which is kind of same kind of what is challenges we face in the field in the actual roads as well, right? So it depends actually. Like in some facility, it is more controlled, and some of them like more close to that of the what to say to that of the field construction. And also we there is another issue with the APT is that the compaction effort. So he's really like extremely correct in that case, because for the APT we have a constrained length of the payment, right? So the compaction effort will be different at both ends of the payment. So to compensate that, what we do is like we give a specific length of the payment which is not considered for the analysis. That will be considered as an outside zone, and only the middle portion will be considered for the testing and analysis of the payment. So that's how we try to eliminate these kind of anomalies which could come in the APT facilities, and try to maximize the like to make it as closely resemble as that of the real payments in the field. And moving to the next question is the load applied in an APTF is a constant load, tire pressure, wheel path. How do the results simulate the actual spectrum of axle loads and tire pressures, and also the transverse distribution of the load? Yes, so I'll break down his question. So there are different factors he's saying about. So one is the load, tire pressure, and wheel path. So coming to the wheel path, as I mentioned, the HVS, most of the HVS coming now has the facility, has the feature of wandering. So that is, using the wandering system, we are trying to mimic what is happening in the field. It will not be accurately simulate with the like replicate the field condition, but we are trying to match it as closely as possible with a different kind of distribution. For in our case, we use a normal distribution with the mean as the central point, and so that's how we address the wheel path issue. And the tire pressure, he's right. Like we cannot have like a different at least in our HVS machine, we cannot dynamically adjust the tire pressure during passes. It should be a constant value. So that is one thing. Like we still have to address that, and also the load conditions. But again, these the APT facility, like our main goal is one of our main goal is to compare between different materials. So, for example, we have labs associated with us, such as which focus on the asphalt binder and mixture, which is called as ABML lab, and we have a geotechnical lab, and we have an NDE lab. So we use different mixtures from these recommended by the ABML lab in our test section, which has the same structure, substructure. Only difference is the different asphalt mixtures. It could be polymer modified or bio-oil modified, anything. So for the comparison of these materials, this doesn't matter. We can use a same constant load and tire pressure. In that case, this works for us. But he's right. In case if we are going for like calibration models and all, then he's extremely right. We need to consider the limitation of the constant load and tire pressure. So that's all for that. And the third question is the performance of a pavement depends on the moisture content of the subgrade soil, which varies widely for any project road. How do APTF consider the effect of variation in performance with variation in subgrade soil under varying subgrade moisture condition for a project road under varying construction quality, density of compaction? This is a great question, actually. So, uh, density of the compaction. So that the variability in density of compaction is really critical, and it happens very frequently. Actually, even in our case, when we look at the DCP test. So I don't know how many of you are familiar with that. So we have testing called DCP, dynamic confidentiality testing. So that using that we can kind of say like what is the compaction level across the depth of the unbound layers. So we try to look at that, and it's not consistent. And also like even after considering the confining impact along the depth, it's not, we could understood that it's not consistent across the depth. So there is a variability in the density of the compaction, and and also the moisture levels. For the moisture levels, our facility is not indoor facility; it's an open facility. So we expect like with the rain, precipitation, like it's going to vary the moisture content in the subgrade layer, and we are trying to capture every climatic impact. That is the main reason we have a open outdoor APT facilities. But most of the facilities are indoor facilities, which as he mentioned, like which controls all of these factors, like which maintains a constant factor for moisture and all. But in our case, it is different, and also we have plans to conduct uh, so our test sections are constructed such that it can be flooded. So we can pump water to the unbound layers and can be flooded. The subsurface can be flooded, and we plan to load the sections under flooded conditions. So that's how we try to address the impact of the moisture contents. Like I know, like it's in two different extremes. Like one is the flooded condition and one is the normal condition. But we expect, like with the emergence of a crack over the pavements, we get more and more moisture in the subsurface level, and we could cover a wide range of moisture content during our course of testing time. With that, I move to the fourth question. How do you consider the variation in loading, rest period, recovery in APTF under varying loading conditions and temperatures? Again, like a very relevant question. So rest period, his question is focusing on the loading. I understand it is the load levels, and rest period and recovery. So rest period and recovery, which is very critical for the asphalt layer. So in our condition test plan, like we are not controlling the temperature. So that is the main features. We don't have a insulated side covers, so that we don't control the temperature. So temperature is the ambient temperature, and it fluctuates with the weather conditions. And so we are not controlling the pavement temperatures, first thing. And the rest period is still a factor, actually. So with the temperature impact of the rest period is fine. We take care without controlling the temperature, but the speed of the HVS vehicle is constant. We are keeping it as a constant, do the entire test using a constant speed. And we know, like, that is a limitation with our current testing plan. We could see that clearly in our pavements with asphalt treated base layer, which has a very thick layer with the asphalt binder. So in that case, we could see the impact of the rest period, and we have tried a small experiment with comparing the impact of different traffic speeds. Like we considered 3 different levels of speeds and tried to compare the responses, payment responses. So, but I know, like, it's not going to, like, for our long-term performance evaluation, we'll be using only single speed and the load condition. So it's still a limitation for our current study. And moving on to the 5th question, what are the different layers considered for the analysis in an inverted pavement? Is a thin BC considered as a structural layer? When back calculation is carried out considering 3 layers, what are the 3 pavement layers considered in an inverted pavement analysis, which has the following layers: fill, subgrade, subbase, FTR or CTB, and granular crack relieving layer or SAMI layer, and 30-40 mm BC. Yeah, so in our case, we haven't carried out the back calculation for the inverted payments. So the results I presented was from the pressure cell readings. So we have conducted the SW deflection, but we haven't moved forward to do the back calculation analysis. And I think, like, his question is really relevant, because we also have a very thin asphalt layer, which is around 1.25 inches, which is very thin. So, so for our analysis, we might need to, like, that level of thin layer cannot be captured, like, during a back calculation process. So we could possibly, like, we didn't have a final plan to do how to analyze the back calculation. So it's still under consideration. We haven't gone that forward to do the back calculation analysis. So with that being said, I have the 6th question. How are individual material test result integrated in a payment system analysis. Do the resilient modulus of granular bituminous mixtures computed under ideal test condition for a material in lab represent the actual moduli in the field as constructed? Again, like very relevant questions. So this is our one of our first step in our APT facility. So as I mentioned, we have asphalt binder mixture lab, which provides the specification for the mixtures. So we already have the material properties from the lab, and we have the material properties from the field samples, like code samples, and also we have the estimated material properties using non-destructive methods such as FWD or LWD. So we try to compare these results, and we found a huge difference between the laboratory results and even with the core results. So there is significant difference between it. Could be either with the compaction, and there was actually a variation in the air void level. So it is different with the laboratory results. And again, we are trying to develop a master curve for the asphalt layers for the HMA layers using the back calculated moduli. So we try to do the FWD testing under different frequencies using different buffers, so that we can capture a wide range of frequencies as well as temperatures. So using that, we try to develop a master curve based on the back calculated moduli and to compare it with the master curve for the mixtures from the lab. So we still need to go there's a long way ahead, like to compare all these results from the lab and the actual the payment properties from the field. And I'll move on to the last question, which is the 7th question. How are the LWD moduli values differ from back calculated FWD moduli and lab moduli values? If the bituminous layer consists of 100 mm dBm plus 50 mm dBm2 plus BC 50 mm, how will LWD or FWD give the moduli of the different bituminous layers? So that's again like the answer is like for the PTF at Turner-Fairbank, we haven't done much of a back calculation process. We're still collecting the SWD raw data. And from my experience, like in my previous experience, so it is really hard to distinguish between two different materials, like especially the binder layer and the surface layer. So I know like the DBM and BC is typically the surface layer, right? So it is difficult, and in our case in PTF we have a 3 test lanes which has an asphalt treated base in that. So in my understanding, it will be extremely difficult to differentiate between between the modulus of these 2 layers, but we didn't try this back calculation yet, so we are still figuring out like which method we need to use for the back calculation, and I mean like which softwares, and we are still figuring out like to do to finalize the method. So with that being said, I think I addressed all the 7 questions by Virago sir. And again, like thank you so much, sir, for all these questions. These are really good questions, actually. Thank you, sir. Gautam, is there any other questions?
Yeah, Ashith, thank you. Something here. Audible? I'm audible?
Yes, I can hear you.
Yeah, okay. I'm sure the listener, even for your PhD, would not have faced such a long questions. Viran sir is always like that.
I'm really happy to see him actually, because I met him a couple of months back. He actually visited our lab actually. So
yeah, I know. He told me also.
Yeah.
He said that that he wanted to attend some program at 11 o'clock. That's why. Otherwise, he wanted to complete and attend that this one.
I see.
Yeah, definitely. Listen, the congratulations once again that Ashith, it was a very good presentation. And
Thank you so much, sir.
yeah, we also raised so many practical issues. That is more important here.
Yes.
And probably you may be knowing that we had even in 70 or 80s, we had a accelerated payment testing sessions with the Professor Gesto, Bangalore University.
I see.
Yeah, that was the first, and of course, now that is not functioning. Of course, it is almost in the damaged situation. But as you mentioned, we have one at Sierra, right? But our people are not extensively. We are not using that one. But recently, ministry supported 3 projects. So one to IIT Kharagpur, and another one to IIT Tirupati, where Krishna Prabhurna is working on it.
Bilgiri, sir. Yeah.
Yeah, Bilgiri. He has constructed the track, and then the setup is also ready, and he started doing experiment on it. And third one, we have one in Highway Research Station in Chennai. That again, recently it was started functioning. So we have currently 3 plus CRRA. 4 it's available in India. It is available in India, and they are ready to take up even a project from outside also. That is what Krishna shared that one with me. And if someone would like to do some project, he will give that facility there. And more or less listen, it was in the similar a setup which you presented here. But we have to go a long way. Definitely, we have to go a long way to utilize that one to its fullest, the possible experiments. Thank you once again, Ashith. Probably listening, you can also give guidance to this 4 centers and into NATPAC also again, so that we can take your concepts forward.
Sure, sir. So I have met Dr. Bilgiri. So he came to attend last TRB conference, and he announced the program actually. So then I came to know they have a facility in IIT Tirupati, right? It's in Tirupati.
Yeah, it is in Tirupati.
Okay.
And it is more or less like a PPP model. Like listen, I think even some private participation is also there. I think some automobile agencies are also involved in that project.
I see. Okay.
That's good.
Okay. Yeah. I'm really happy to assist in any ways, like either in instrumentation or any phase of these facilities. I'm open to that actually.
Thank you, Ashith.
So I think I have another question from Shijit. How to correlate small-scale accelerator results with large-scale payment life? So I am trying to understand the question. Okay, so small scale accelerated results. That means I think what he means is the APT results with the actual field payment life. So so as I mentioned in the slide, so we are trying to address there are 3 aspects. You can understand it let me put it in this way. So there are 3 aspects. So first thing is you can develop correlation between the index-based laboratory test so that you can project it to the for comparison of different materials. So you have 2 materials. So you have the index parameters, and you can try to estimate the fatigue life or rating life using the correlations. So that is one way. And the second way is we are trying to improve the prediction models the transfer functions. So which again is like take care of the, we are not directly addressing the field life. We are not directly correlating with the field life. We are trying to improve the prediction model, so that it will take care of the field intricacies. And the third one will be what was that? The again, like coming to coming to the improvement of the payment response model. So, for example, like for the these inverted payment structures, we cannot use a normal linear elastic analysis software. There will be a huge error in that because of that specific feature of that kind of payment structures. So we are trying to improve the models basically, and also to correlate with the index-based test, not directly correlating with the actual field payment. So, and I know like there will be a difference between a actual payment and with a APT facility, but we are trying to come as close as possible with a full-scale payment. I mean, not full-scale payment, actual payment, as close as possible. So that is the goal. So I hope I addressed your question. If not, you can unmute yourself and ask me.
Dr. Ashith, thank you for your presentation and queries. I mean, the questions, I mean, the answers which you have asked for the questions. So now we move to the end of the session.
Now, I would like to call upon Shijit PP, Junior Scientist, to propose the vote of thanks.
Good morning, all. On behalf of KSCSTE-NATPAC, I would like to express my sincere gratitude to each one of you for joining the 21st Transpedia Research Talk on topic From Lab to Field, the role of accelerated payment testing in modern payment designs. So it has been an exciting and outstanding session. First and foremost, I would like to express my deepest appreciations to our distinguished speaker, Dr. Ashith Marath, for sharing his valuable research finding with us. So your major research findings in the accelerated payment testings and its calibrated payment designs modules and its mechanism, these all are fantastic. So once again, I thank you, Dr. Ashith Marath, for delivering such a wonderful presentations. So I want to express my sincere thanks to all attendees for your active participations and interactions. We believe that our Transpedia Research Talk series is getting beneficial to students, academicians, and working professionals, etc. So our heartfelt thanks to Dr. Viran sir and Dr. Samson sir for their active participations, and also special thanks to Dr. Vishnu for attending these sessions. Furthermore, a big thanks to our director, division heads, and Transpedia coordinating teams for making this event possible. We encourage all the participants to join in the upcoming online series organized by KSCSTE-NATPAC. Thank you. Thank you all.
Thank you, Ashith.
Thank you.
Thank you.
And as I mentioned, like feel free to reach out to me in my email if any questions are left. Don't hesitate to do that. Okay. All right.
Okay.
Thank you so much, and see you. Bye. Take care.
Bye-bye.